Welcome to Scoli Sleep Stories. Before we begin, take a moment to get comfortable, let the day soften around you, and settle in for a calm documentary made for curious minds. If these stories help you rest, learn, or simply enjoy a quieter part of the day, please consider liking this episode and subscribing to the channel. Now, when you are ready, let us begin. Chapter 1: The Daily Arrival of Night. Late afternoon settles gently across the familiar world. Sunlight, once bright and direct, has begun to turn amber. It rests on walls and windows, catches along the edges of leaves, and stretches the shadows of trees across gardens, sidewalks, and quiet roads. A room that seemed evenly lit at midday now holds small pools of shade. Colors become warmer for a little while and then softer. Outside, the sounds of the day begin to change. A distant door closes, footsteps pass and fade. Birds make their last journeys between rooftops and branches. Somewhere water moves through a pipe, dishes touch softly in the kitchen, and a low murmur of conversation drifts from one room to another. The world has not become silent, it has simply changed its tone. Inside the body, evening is arriving too. This inner evening does not begin at one exact moment. Darkness is not a switch that instantly changes wakefulness into sleep. The body notices the passing day gradually, gathering information from light, activity, meals, temperature, and the ordinary patterns of life. Many small signals come together, like clocks in different rooms quietly agreeing on the hour. Throughout healthy human life, sleep returns again and again. Infants sleep in many periods scattered across day and night. Children develop different patterns as they grow. Adults often gather more of their sleep into the nighttime, while sleep may become lighter or differently timed in older age. The details change, yet the rhythm remains. Activity gives way to rest, and rest eventually opens again into activity. Sleep may appear still from the outside, but it is not a shutdown. Nor is it an empty interval in which nothing happens. It is an organized biological state. During sleep, patterns of brain activity change. Awareness of the outer world becomes reduced. Muscles alter their level of tension. Breathing and circulation follow shifting rhythms. Hormones rise and fall. Body temperature is regulated, while the immune and metabolic systems continue their careful communication. Life does not pause during sleep. It changes its manner of working. The daily pattern that helps arrange this change is called a circadian rhythm, an internally generated rhythm lasting approximately 24 hours. The word circadian comes from Latin words meaning about a day. It is not a rigid clock with a loud tick. It is closer to a quiet tide, rising and receding in a pattern that is steady, yet responsive to the world. Circadian rhythms influence far more than the time when sleep begins to feel welcome. They help shape alertness, appetite, digestion, hormone release, and body temperature. At certain hours, the body is more prepared to be active. At others, it begins to favor quieter forms of work. These rhythms are shared, but they are not identical from one person to another. Some people naturally feel clear and alert earlier in the day. Others find that their strongest period of wakefulness comes later. This tendency is called a chronotype. Chronotype is one reason morning may feel spacious and inviting to one person, while evening feels especially natural to another. It does not divide humanity into two perfect groups. People lie along a wide and gently shifting range. Age, environment, daily routines, and individual biology all help shape the timing. Even within one life, the pattern can change. The inner day of infancy is not the same as the inner day of childhood. The rhythms of adolescence may differ from those of adulthood, and timing may shift again in later years. Sleep is universal across healthy human life, but its timing and structure continue to develop as people grow and age. Beneath all this variation, the body keeps time. Nearly every organ and tissue contains a local biological clock. These local clocks are not tiny clock faces hidden inside the body. They are repeating chemical and genetic processes within cells. Certain molecules increase, decrease, and influence one another in cycles. Together, these cycles help tissues carry out particular tasks at suitable times. The liver follows recurring signals connected with food and energy. The digestive system responds to familiar patterns of meals. Muscles, fat tissue, the heart, and many other parts of the body move through daily cycles in the ways their cells perform their work. It is a wide community of clocks, distributed throughout the body. Helping to coordinate this community is a small timekeeping center in the brain. It is called the suprachiasmatic nucleus, often shortened to the letters SCN. The SCN is a small group of nerve cells, or neurons, within a part of the brain called the hypothalamus. Its full name is long, but its role can be pictured simply. Imagine a calm conductor helping many sections of an orchestra remain within the same piece of music. The conductor does not play every instrument. Each section has its own part, its own activity, and its own sound, yet the conductor helps them remain coordinated. In much the same way, the SCN does not perform every daily task of the organs. It helps coordinate their timing, keeping many separate rhythms in a useful relationship with one another and with the world outside. The SCN receives especially important information from the eyes. Specialized cells in the eyes report environmental light to the circadian system. They help the brain recognize whether the outer world is brightening, remaining bright, or growing dim. Light and darkness are the strongest outside timing cues for the human circadian rhythm. Morning light helps align the inner day with the day outside. Evening dimness helps signal the approach of biological night. This daily adjustment matters because the body's internal rhythm lasts approximately, rather than perfectly, 24 hours. The turning planet provides a regular guide. Other cues join this quiet conversation. Meals carry timing information. So do physical activity, changes in temperature, stress, and social schedules. A familiar meal, an afternoon walk, the warmth of daylight, and the recurring patterns of work or companionship can all influence the body's sense of time. No single cue acts entirely alone. The rhythm of a human day is woven from both biology and experience. As evening develops, the strong alerting signals associated with daytime usually begin to weaken. This change may be subtle. Attention may become less outwardly focused. The bright edges of the day soften. The body is not being forced abruptly into another state. It is being guided toward one. Under dim conditions, production of a hormone called melatonin begins to rise. A hormone is a chemical messenger carried through the body. Melatonin helps announce that biological night has begun. It is sometimes described simply as the substance that causes sleep, but its role is gentler and more precise than that. Melatonin does not single-handedly make a person unconscious. Instead, it provides timing information. It is like a lamp being lowered in a theater before the next part begins. The dimming lamp is an important signal, but it is not the whole performance. In the same way, rising melatonin is one part of a much larger arrangement, unfolding throughout the brain and body. At around the same time, core body temperature begins a gradual circadian decline. Core temperature means the temperature of the body's internal tissues and organs, rather than the warmth felt at the surface of the skin. This cooling unfolds slowly through the evening and night. The lowest point often comes much later, near biological morning. After that, temperature begins to rise again as the body moves toward wakefulness. The evening decline may be modest, yet it belongs to a broad and carefully coordinated pattern. Hormonal signals alter their timing. Digestion, alertness, and energy use enter their nighttime phases. The body does not stop maintaining itself. It simply rearranges its priorities. This is why the word reset can be useful, provided it is held lightly. Each night offers renewal, regulation, and preparation for another day. Yet the body does not erase itself or return to a perfectly blank beginning. Memories remain. Cells carry their histories. Muscles and organs continue from where the previous day left them. The body is always maintaining, always adjusting, and always carrying life forward. Even during the brightest hours, some repair and regulation are underway. Even during the deepest part of night, some systems remain watchful and active. Day and night are not separate machines. They are two phases of one continuous rhythm, like the bright and shaded sides of a turning landscape. Beyond the window, amber light gives way to blue-gray dusk. Details at a distance become less distinct. Windows glow softly. The air cools. Sounds that once stood apart begin to blend into a quieter background. Within, countless clocks continue their nearly silent work. The eyes have reported the fading light. The master clock in the brain helps coordinate the timing. Local clocks in tissues and organs adjust their patterns. Melatonin carries its message of biological night. Core temperature begins its long, gentle descent. Nothing has happened all at once, and nothing needs to. Night arrives by degrees, both outside and within. The change is gradual enough to be almost unnoticed. One shade deepens into another, one sound fades, and a quieter sound takes its place. The inner world follows its own unfolding rhythm, moving not with a sudden command, but with many small adjustments working together. And as these internal clocks continue their quiet work in the background, two steady influences begin to meet. One is the nightly timing signal of the circadian clock. The other is the sleepiness that has accumulated across the waking day. Together, patiently and gradually, they guide the body toward the threshold of sleep. Chapter 2: The Two Forces That Lead Us to Sleep. Across the waking day, sleepiness gathers like a quiet tide. In the morning, after a restful night, the water may seem far from shore. The mind may feel clearer, the body readier to move, and the hours ahead open and spacious. Yet from the time wakefulness begins, a gentle pressure starts to build. At first it may be scarcely noticeable. It does not need to announce itself. It simply gathers as the day unfolds. Through breakfast and conversation, through work and wandering thoughts, through movement and stillness, sunlight and shade. Scientists often describe this growing need for sleep with a model based on two interacting influences. The first is called sleep pressure. It is also known as the homeostatic sleep drive, or process S. Homeostasis refers to the body's tendency to maintain a changing balance. Just as thirst tends to grow when the body needs water, sleep pressure generally increases with time spent awake. Then, while we sleep, that pressure gradually falls. This does not mean wakefulness is a problem that must be corrected. Wakefulness and sleep belong together. Each creates the conditions for the other, as two parts of a continuing rhythm. The day allows us to move, learn, notice, remember, and respond. As those waking hours pass, the need for another period of sleep slowly becomes stronger. One chemical associated with this process is called adenosine. Adenosine is present throughout the body and takes part in ordinary cellular activity. In parts of the brain, it accumulates during wakefulness. It can act on receptors, which are small receiving structures on cells. When adenosine acts on certain receptors, it favors sleepiness and reduces some of the signaling associated with alertness. We might imagine adenosine as fine grains gathering in an hourglass. One grain is too small to notice, yet as the waking hours continue, more grains collect. Their combined weight becomes easier to feel. The eyelids may seem a little heavier. Concentration may require more effort. Thoughts may begin to move along slower, quieter paths. The body may become more willing to be still. The hourglass is a useful image, though the real biology is more intricate. Adenosine is not the only substance involved in sleep pressure, and no single chemical can fully explain why we become sleepy. Many brain regions, chemical messengers, and body systems take part. Scientists continue to study how all these elements interact. Sleepiness is not held in one molecule, one place, or one hidden chamber. It emerges through a wide network of processes working together. Caffeine touches one part of that network. It promotes alertness mainly by blocking adenosine receptors. For a while, this can prevent part of adenosine's message from being received. But caffeine does not remove all the adenosine that has accumulated, and it does not erase the underlying need for sleep. The grains have not vanished from the hourglass. For a time, some of their signal is simply less clearly heard. So one force gathers through the day, but sleep pressure is only part of the story. If it acted alone, sleepiness might rise in a simple, steady line from morning onward. We would become progressively sleepier with each passing hour, without moments of renewed alertness. Human experience is rarely so smooth. Someone may feel tired in the late afternoon, then unexpectedly brighter in the evening. Another person may stay awake later than usual, and notice a peculiar stretch of alertness, even after a long day. The body may be carrying a strong need for sleep, while another influence continues to support wakefulness. To understand this, we meet the second force. It is called circadian timing, or process C. Circadian means approximately a day. The circadian system is the body's internal timekeeping network. It coordinates patterns that rise and fall across roughly 24 hours. Near the center of this network is a small group of cells in the brain called the suprachiasmatic nucleus, usually shortened to the letters SCN. The SCN receives information about light through the eyes. and uses that information to help coordinate many daily rhythms. It is sometimes called the master clock. Yet it is not a rigid clock, controlling every moment with a sharp and mechanical tick. It is more like a patient clock keeper, helping the body's rhythms remain aligned with one another and with the changing world outside. If sleep pressure is a rising tide, the circadian system is something like a lighthouse and clock keeper beside the shore. It does not create the tide. Instead, it marks the changing hours and helps determine when the rising water is most likely to carry the body towards sleep. One force gathers through the day, the other keeps time through the day. Without signals from the outside world, the human circadian clock does not run at exactly 24 hours. Its timing can drift. Daily light helps keep it aligned with the day and night cycle. Through the eyes, the SCN receives news of the outer world. It learns whether morning has arrived, whether daylight remains, or whether the environment has grown dim. Using this information, it helps coordinate the timing of melatonin and many other daily rhythms. Melatonin is a hormone that carries a message of biological night. It usually begins rising under dim conditions before a person's habitual sleep period. Toward morning, its levels generally fall again. Melatonin is sometimes described as though it were an on and off switch for sleep. Its role is gentler and more subtle. It is better understood as a signal that biological night has begun, rather than a command that instantly produces sleep. It tells the body something about the hour. It joins a wider conversation among the brain, the body, the environment, and the accumulating pressure to rest. Bright light in the evening can shift or suppress this melatonin signal. The effect is not identical in every setting or for every person. It depends on the brightness of the light, how long it lasts, when it appears, its wavelength, and the biology of the individual receiving it. The circadian system is responsive, but it is not a simple meter. It interprets patterns of light over time, adjusting its timing gradually. Throughout the waking day, circadian signals also help support alertness. These signals can temporarily oppose the sleep pressure building beneath them. Even while the tide rises, the clock keeper may continue to signal that it is time to remain awake. This helps explain the familiar evening second wind. A person may feel weary, and then for a while, become more alert again. The accumulated sleep pressure has not necessarily disappeared. The circadian alerting signal may still be strong enough to hold sleepiness at a distance. Like a lighthouse beam passing over darkening water, it briefly makes the way ahead seem clearer. The tide is still rising, but the light remains. Later, as biological night deepens, the circadian alerting influence usually eases. Melatonin continues carrying its quiet message. The circadian system becomes more supportive of sleep, while sleep pressure remains high after the many hours of wakefulness. The two forces do not operate as independent switches, each clicking separately into place. They interact continuously. One reflects in part how long the brain and body have been awake. The other reflects where the body is within its daily rhythm. Sleep becomes more likely when accumulated pressure is strong, and the circadian clock is no longer firmly promoting alertness. One force gathers through the day, the other keeps time through the day. Together, they shape when sleepiness rises, when alertness remains, and when the boundary between the two begins to soften. Their meaning differs from person to person. Some internal clocks tend toward earlier timing, while others tend toward later timing. Sleep also varies across ages, individuals, and nights. Recent sleep can make a difference, as can illness, medication, stress, physical activity, and individual biology. No 2 days create precisely the same tide. This natural variation helps explain why sleep does not always arrive at a perfectly predictable moment. Someone may have been awake for a long time and carry strong sleep pressure, yet remain alert because the circadian system is still supporting wakefulness. At another time, the circadian clock may be signaling biological night while sleep pressure remains lower, perhaps because of sleep earlier in the day. The two influences can overlap neatly, or they can meet somewhat unevenly. There is nothing strange about this. The timing of sleep is not produced by a single lever. It emerges from cooperation between systems, each responding to different kinds of information. Sleep pressure remembers in its own biological way the duration of wakefulness. Circadian timing remembers the hour. The tide and the clock keeper continue their patient work. Grain by grain, hour by hour, the pressure for sleep grows. Adenosine participates in that gathering need, while many other processes add their quieter contributions. The SCN receives the pattern of light, and helps coordinate the rhythms of biological day and night. Melatonin carries news of darkness. The circadian support for alertness gradually recedes from its daytime strength. Sleepiness may also be colored by everything the day has held. Illness can make the body feel more tired. Some medications can change alertness. Stress may make sleepiness harder to notice, even when the need for rest is present. Activity, previous sleep, and individual biology all become part of the pattern. Even so, beneath these changing influences, the two broad forces remain useful guides. Sleep pressure rises with wakefulness and falls during sleep. Circadian timing helps place wakefulness and sleep within the daily cycle of light and darkness. They work together, rather than standing apart. No single moment must carry the whole transition into night. Evening can arrive gradually. A room becomes dimmer. Sounds seem farther apart. The day's sharp edges begin to soften. The body does not have to leap from wakefulness into sleep. It can approach by degrees. The tide has been rising since morning. The clock keeper has followed the changing light. Now their signals begin to agree. The long waking day has created a need for rest, and the internal rhythm is beginning to mark the hour as night. Attention loosens from the edges of the day. Thoughts that were arranged in firm lines begin to wander into softer shapes. The outside world feels a little less urgent, while the quiet, inner world becomes easier to notice. Still, the passage is not always perfectly smooth. Alertness may brighten briefly and then fade. A thought may rise, drift away, and return once more. The body may feel ready before the mind, or the mind may grow quiet while the body continues settling. The two forces do not demand an exact crossing. They simply help make the crossing possible. Sleep pressure has gathered through the day. Circadian timing has kept the hour. Now, as dimness deepens, they draw nearer to one another, not with a sudden command, but through steady cooperation. At their meeting place lies a subtle threshold. Wakefulness begins to loosen. Muscles prepare to soften. Thoughts grow less firmly connected to the world around them, and beyond that quiet boundary, the first gentle stages of sleep are ready to unfold. Chapter 3. Crossing the Threshold. Thoughts that were arranged in firm lines begin to soften at their edges. A sentence starts clearly, follows its course for a little while, and then seems to lose its ending. Another thought appears, perhaps connected to the first, perhaps not. It carries the faint shape of an idea, then dissolves before it can be examined. There may still be awareness of the room. A distant sound remains recognizable. The weight of the body against a familiar surface can still be felt. Yet these impressions no longer ask for the same attention. They arrive, linger briefly, and pass on. Sleep does not always come like a curtain falling in a single instant. More often, it is a gradual crossing. Wakefulness becomes less steady. Attention turns inward. The clear boundaries between thought, sensation, and imagination begin to blur. Because this crossing is gradual, it can be difficult to identify the exact moment when waking ends and sleep begins. There may be no distinct dividing line. Instead, there is a quiet region between the two, like a shoreline where water and land meet in shifting patterns. One moment belongs mostly to wakefulness, the next belongs a little more to sleep. The first recognized stage of this journey is called N1. It is the opening stage of non-REM sleep. The letters REM stand for rapid eye movement, a later kind of sleep with patterns of its own. Non-REM simply refers to the stages outside that rapid eye movement period. N1 is the lightest of these stages, a gentle first step away from ordinary waking awareness. During the day, the waking brain produces patterns of electrical activity suited to attention, movement, planning, and response. These patterns are often called brain rhythms or brain waves. The words describe the coordinated electrical activity of large groups of brain cells. As N1 begins, the rhythms associated with wakefulness give way to slower mixed-frequency activity. This is not a complete shutting down. The brain remains active, but its activity is becoming organized in a different way. It is no longer tracking the outside world with the same steady precision. The room is still present, but it is beginning to matter less. Responsiveness gradually decreases. A sound may still be heard, yet seem less important. A voice in another room might be noticed without its words being followed. The soft hum of air, the settling of a building, or the faint passage of traffic may merge into a single background texture. One sound may rise briefly into awareness, then the next may pass without notice. The eyes also begin to change their behavior. Behind closed lids, they may move slowly in gentle rolling motions. These are not the rapid movements that give REM sleep its name. They are slower and quieter, part of the body's gradual departure from active wakefulness. Muscle tone is the small amount of tension that remains in muscles even when they are not making a deliberate movement. During N1, that background tension starts to ease. The jaw may become looser. The shoulders may settle. The hands may rest with less intention, as though they no longer need to hold their daytime shape. The body is not becoming completely motionless. It is simply releasing some of the readiness that belongs to the waking day, less prepared to act, less concerned with the next task, more willing to be still. Awareness often fades unevenly through all of this. It is possible to notice one sound clearly and miss the next. A person may briefly recognize a thought, then lose track of where it began. For a few moments, the mind may seem to be both near the room and far from it. A familiar sensation may remain clear, the position of a hand, the touch of fabric, the faint sound of breathing. Then, without any obvious signal, that sensation may fade from attention. It has not necessarily disappeared. It is simply no longer being followed. This uneven fading helps explain why light sleep can sometimes feel like wakefulness. A person may pass through N1 and later believe that no sleep occurred at all. Because some awareness remains, and because thoughts may still seem present, the boundary can be mistaken for continued waking. Yet even a partly watchful feeling can accompany genuine light sleep. N1 is typically brief, though there is no single duration that applies to every person or every night. Its timing can vary with sleep pressure, age, surroundings, medication, health, individual biology, and many ordinary differences from one night to another. When sleep pressure is strong, the passage may be swift. At another time, it may unfold more gradually. Nothing about the transition needs to be perfectly uniform. The body can approach sleep, drift lightly, and return for a moment toward clearer awareness. Then it may begin crossing again. Sleep onset is less like stepping through a doorway and more like moving through a broad, dim landscape whose borders are difficult to mark. There may be a little wakefulness here, a little sleep there, and a quiet mingling between them. Within this landscape, some people experience brief, dreamlike impressions. Scientists often call these experiences hypnagogic imagery. Hypnagogic simply means occurring while falling asleep. The imagery may be visual, but it does not have to be. It can include sounds, sensations of movement, vague shakes, voices, or fragments of an incomplete scene. A soft pattern may appear and vanish. An indistinct shape might drift through the mind like a reflection on dark water. There may be the impression of a half-heard phrase spoken by no clearly identified person. A staircase, a window, a passing face, or a stretch of unfamiliar landscape may form for an instant, without becoming a complete story. Sometimes there's a feeling of floating, turning, or gently moving through space, even though the body remains still. At other times, an ordinary thought changes without warning into something more image-like. A memory of walking along a path may become the path itself. Then the path may fade before it leads anywhere. A word becomes a color. A remembered room opens onto an unfamiliar sky. A sense of motion appears without a destination. These impressions do not need to make sense. They arise at a time when awareness is no longer arranging every experience into a clear and continuous order. Thought, memory, sensation, and imagination may briefly overlap, then separate, then disappear from notice. Such experiences are not necessarily dreams in the same form as the longer, vivid dreams often associated with later REM sleep. They belong to the transition, where waking thought and early sleep can mingle. The mind is loosening its careful hold on sequence and logic. A voice may offer only one word. A scene may have no beginning and no conclusion. Not everyone notices hypnagogic imagery. Some people encounter it often, others only occasionally, and some hardly at all. Even when it occurs, it may leave no memory by morning. Like so much of N1, it can pass too lightly to be recorded as a clear event. There is no special meaning required. A passing shape can remain only a passing shape. A drifting sensation can simply drift away. These are among the varied, ordinary experiences that may accompany the beginning of sleep. Another common experience near sleep onset is a hypnic jerk. This is a brief involuntary contraction of a muscle or group of muscles. A hand, arm, shoulder, or leg may move suddenly. Sometimes the movement arrives with an impression of stumbling or falling, though it may occur without any accompanying image at all. The movement may briefly bring the room back into focus. Awareness brightens for a moment. The body settles again, then the crossing can continue. Hypnic jerks are common and usually harmless. They are small movements that can occur near sleep onset, while muscle activity and awareness are changing. Not everyone notices them, and they do not happen every time a person falls asleep. There are popular stories claiming that such a movement is the body checking whether someone is still alive, or reacting because it believes the body is falling or dying. These explanations are not supported by scientific evidence. A hypnic jerk does not need a dramatic meaning. It is generally only a brief contraction near the edge of sleep. Afterward, the transition can continue as quietly as before. The hand rests again. The half-formed image disappears. A sound from the room reaches awareness, then drifts beyond it. N1 asks very little of the sleeper. There is no task to complete and no exact instant that must be recognized. The body does not require the conscious mind to supervise the crossing. Systems that have prepared through the evening continue their work. The circadian clock carries its message of biological night. Sleep pressure remains present. Networks of the brain begin shifting toward the patterns of non-REM sleep. The world outside has not vanished, but it is losing its central place. Sounds that once stood apart begin to blend. Physical sensations remain, though they may no longer be named. The mind releases the habit of checking one moment against the next. Awareness may brighten once more, then soften again. A thought may seem important for a moment, only to lose its shape. The room may return in outline, then recede. This gentle movement between clearer and quieter awareness is part of the threshold. Sleep need not arrive in one perfect, uninterrupted descent. It may approach in small waves, nearer, then farther, nearer again. A thought begins and its ending is no longer needed. Perhaps there is a dim reflection, a word without a speaker, or the feeling of moving along a road that has no map. Perhaps there is only a gentle absence of clear attention. Each possibility is ordinary. Each belongs to the varied ways human awareness can loosen from the waking day. And perhaps nothing noticeable occurs at all. There may be no image, no sudden movement, no memorable sign. Wakefulness simply becomes thinner. The room grows less defined. The next clear moment may come only later, without any memory of the crossing itself. This is one reason sleep onset can be so difficult to locate. The part of the mind that might observe the transition is itself becoming less attentive. It cannot always mark the instant when awareness fades, because the ability to mark that instant is fading too. The shoreline shifts quietly beneath the traveler. One moment still carries the shape of the day, another is already touched by sleep. Soon, even the shoreline becomes less distinct. Muscles continue to relax. Responses to the room diminish further. The partly waking quality of N1 begins to settle into a steadier form of sleep. There is no need to know precisely when the change has happened. The threshold may pass without announcement. Wakefulness simply becomes less solid, while sleep becomes steadier beneath it. The room remains where it was. The distant sounds continue. Yet clear attention has loosened its hold, and the first gentle stage has carried the sleeper away from the surface of the day. From here, the journey can continue beyond the shallow edge of N1, moving from the shifting shoreline into the deeper, quieter waters of non-REM sleep. Chapter 4. Descending into Deep Sleep. Beyond the shifting shoreline of N1, sleep becomes more settled. The last worst fragments of waking thought recede, like faint reflections disappearing from the surface of dark water. Awareness of the room grows quieter. A familiar sound may continue nearby, yet it no longer asks for attention. The body has crossed the first threshold and now enters a steadier region of sleep. This next stage is called N2. The letter N stands for non-REM sleep, meaning sleep without the rapid eye movements that appear later in the night. Modern sleep science divides non-REM sleep into 3 stages, N1, N2, and N3. Older descriptions sometimes divide it into 4 stages, so an older book or diagram may use slightly different names. Yet the underlying journey is much the same. Sleep moves from its lighter edge toward deeper rest, and later rises again. N2 is still considered light sleep, but it is more stable than N1. It is not merely a brief passage on the way to somewhere else. In fact, N2 usually occupies more of an adult night than any other single sleep stage. Across the hours, the sleeper may return to it several times as the larger cycles of sleep gently rise and fall. In N2, the slow eye movements of N1 come to an end. The eyes grow still beneath their lids. Muscles relax further, though the body remains capable of movement. Heart rate and breathing generally slow, following the gradual turn away from the active pace of the day. Body temperature continues to decline as well. This cooling is part of the circadian rhythm, the roughly 24-hour pattern that helps coordinate waking and sleeping. The decline began before sleep arrived, and it continues gently through these quieter hours. It is not a sudden chill, but a carefully regulated change. It is one more sign that many parts of the body are settling together. Yet the brain has not simply switched off. Its electrical rhythms take on distinctive patterns, and two of the most recognizable patterns in N2 are called sleep spindles and K-complexes. Scientists can observe these patterns with an EEG, or electroencephalogram. An EEG is a recording of the brain's electrical rhythms gathered through small sensors placed on the scalp. It does not read individual thoughts. Instead, it reveals broad patterns that appear as large numbers of brain cells change their activity together. On an EEG, a sleep spindle appears as a short burst of rhythmic activity. It rises and fades quickly, like a brief ripple passing across a dark lake. Then the wider surface grows calm again. These sleep spindles are associated with reduced responsiveness to events outside the sleeper. The sound of a building settling, the low passage of a distant vehicle, or another ordinary murmur may reach the senses without fully drawing the mind back into wakefulness. The sleeping brain has not sealed itself away from the world. Instead, it has changed the way incoming information is handled. Sleep spindles are also associated with aspects of memory processing. Their roles are still being studied, and they may serve more than one purpose. For now, it is enough to picture these small rhythmic ripples appearing throughout N2. They are brief and organized, accompanying stable sleep while the brain continues its quiet activity. A K-complex has a different form. It is a large, brief brainwave event, appearing almost like a single broad mark against the gentler background of sleep. A K-complex may arise spontaneously, with no obvious event outside the body. It may also occur in response to a sound or a light touch. It can be imagined as the brain's calm acknowledgement of the surrounding world. Something has happened. The sleeping nervous system has registered it. Yet if the event is harmless, there may be no need to wake. In this way, a K-complex may help preserve sleep while still allowing some monitoring of the environment. The brain remains connected to its surroundings, but not every signal is invited into awareness. A distant sound is noticed and allowed to pass. The dark lake settles once more. Through N2, the sleeper moves farther from the easily disturbed edge of sleep. The heart continues at its quieter pace. Breathing becomes more measured. Muscles rest more fully. There is no sharp border that must be felt as one stage gives way to the next. The change unfolds gradually, as though a path were descending by such a gentle slope that every step seemed level. Then slow waves begin to occupy more of the brain's rhythm. This is N3, the deepest stage of non-REM sleep. It is also called slow wave sleep. On an EEG, N3 is dominated by large, synchronized slow waves. Synchronized means that many networks of brain cells are changing their activity in a coordinated way. Instead of producing the quicker, more varied patterns associated with wakefulness, broad regions rise and fall together. The waves are wide and unhurried. They resemble long ocean swells moving beneath a quiet night sky. One gathers across the water, lifts without haste, and passes on. Another follows. The motion is powerful yet calm. It is simple in appearance, yet formed from the coordinated activity of countless cells. Deep sleep, then, is not an empty darkness. The brain is not inactive. Its activity is differently organized. It is slower in rhythm, larger in scale, and highly synchronized. What looks still from the outside contains an ordered inner pattern. During N3, it is usually more difficult to awaken a sleeper than it is during N1 or N2. Sounds that might have drawn attention earlier may now pass without producing clear awareness. If awakening does occur, the return to alertness may take a little time because the brain has been moving through a state quite different from ordinary waking activity. The rhythms of the body also tend to become slower and steadier. Heart rate is generally lower. Blood pressure is generally lower as well. Breathing tends to be slow and relatively regular, with each breath following the one before it in an even pattern. In and then out. A quiet exchange of air, a pause in the gentle rhythm, then another breath. The muscles remain relaxed during N3, but they are not paralyzed. The body rests deeply while still retaining the ability to move. Deep sleep is not a state of complete stillness. It is a state in which the body's activity has become quieter and more regular. These are general patterns rather than rigid rules. Heart rate and breathing vary from person to person. They may also vary in the same person from one night to another. The exact shape of sleep is never perfectly identical. Each night follows the familiar pattern in its own slightly different way. N3 is usually concentrated in the earlier portion of a typical night. During the first few sleep cycles, slow-wave sleep tends to be longer and more abundant. As the night continues, periods of N3 often become shorter, while other stages occupy more of the sleeping hours. Age also influences this pattern. Children generally experience especially abundant slow-wave sleep. As people grow older, the amount of N3 usually declines. This is one of the normal ways in which sleep changes across a lifetime. The architecture of a child's night is not identical to that of an adult, and the pattern continues to change gradually over the years. No single stage tells the whole story of sleep. Deep sleep is important, but it is not the one superior form of sleep in which every kind of restoration occurs. N1, N2, N3, and REM sleep each contribute to the complete pattern. The body does not choose one stage and discard the others. It moves among them, returning and repeating, making a night from their different rhythms. N2 offers a stable form of lighter sleep, quietly occupying a large part of the night. Its spindles and K-complexes reveal a brain that remains responsive in a carefully altered way. Then N3 brings the broad, synchronized rhythms of slow-wave sleep. Together, these stages show that sleep grows deeper not by becoming empty, but by becoming differently organized. Even the word deep can be understood gently. It does not mean that the sleeper has traveled to a distant place. It describes a state in which awakening is more difficult, and the brain's electrical activity is dominated by large, slow, synchronized waves. The room remains where it was. Sounds may continue beyond the window. Air moves quietly through the lungs. The heart continues its steady work. And within the brain, large communities of cells move through coordinated changes in activity. A slow wave gathers. It passes. Another follows. The body remains settled within the familiar surroundings of the night. Nothing needs to disappear for sleep to deepen. The senses simply respond less readily. The heart and breathing follow calmer rhythms. Muscles remain relaxed. The broad waves of N3 continue to rise and fall. From the outside, deep sleep may appear almost motionless. From within, it is a carefully organized state. The quick patterns of the waking day have opened into broader, slower ones. Many brain cells are changing their activity together, creating a rhythm that belongs especially to these deeper hours. Still, this is only one part of the night. Slow-wave sleep is important, but restoration is not confined to N3. The lighter stages matter too, and other forms of sleep will arrive as the cycles continue. A complete night is formed not from one perfect stage, but from movement among them all. For now, the sleeper rests within the earlier portion of the night, where N3 is usually most abundant. The waves remain wide and unhurried. Breathing continues in its steady pattern. Heart rate and blood pressure remain generally lower. The muscles are relaxed, but not paralyzed. The whole state is quiet, though never empty. It is deep, though never absent. It is restful, though the brain remains active. Beneath the stillness of deep sleep, cells and networks continue their quiet activity. The slow waves pass above this hidden work, like long swells crossing a dark sea. One rises, one falls, and another comes softly behind it. The sleeper remains unaware of these changing patterns. There is no need to follow them, measure them, or notice their passing. The body moves through them naturally, guided by the architecture of sleep. And beneath that calm surface, the living brain remains present. Its activity has not ended. It has entered another arrangement, one suited to the quiet depths of the night. From here, the journey continues inward, toward the subtle cellular and network level work that unfolds while the sleeper rests. Chapter 5. The Sleeping Brain's Night Work. Beneath the broad, slow waves of deep sleep, the brain's night work continues. It may help to imagine a quiet city after the evening traffic has faded. The streets are less crowded, many windows are dark, yet the city has not stopped. Lights remain in a few offices. Water moves through hidden pipes. Signals travel along cables beneath the ground. Small teams adjust equipment, organize supplies, and prepare for the coming day. The sleeping brain is something like this, though far more intricate. Its outward stillness does not mean inactivity. It remains metabolically active, still using energy, and carrying on the chemical work required by living cells. What changes is not whether the brain is working, but how that work is arranged. During waking hours, much of the brain's activity is shaped by the world outside. Light arrives at the eyes, sounds are recognized, muscles are directed, plans are formed, words are chosen, and attention moves from one task to another. In sleep, the balance shifts. Some brain networks reduce their activity, others increase their activity. Still others begin to move together in synchronized rhythms, like distant lamps brightening and dimming at nearly the same time. The exact pattern depends on the stage of sleep. In deep non-REM sleep, large groups of brain cells participate in the slow waves that have carried us into this chapter. At other times, activity becomes faster or more varied. Sleep is not one unchanging condition. It is a sequence of organized states, each with its own patterns, and each contributing to the work of the whole night. Within these larger patterns, many smaller processes continue. Sleep changes gene expression, meaning that it influences which cellular instructions are being read. It affects the production of proteins, the molecules that perform much of a cell's practical work. It also changes cellular energy use, synaptic activity, and the ways neurons communicate with the supporting cells known as glial cells. Glial cells help maintain the working environment of the brain. They assist with nourishment, insulation, chemical balance, and many other forms of support. They are not simply empty packing around more important cells. They are part of the living community of the brain, quietly helping that community remain stable. At the center of communication between neurons are tiny connections called synapses. A synapse is a meeting place where one neuron can influence another. The cells do not usually touch in the way two hands meet. Instead, a minute space lies between them, and signals cross through chemical or electrical activity. Across a single brain, there are an enormous number of these connections. During a waking day, experience changes them. Practicing a movement, learning a name, noticing a familiar path, or responding to an unexpected event may strengthen certain patterns of communication. The brain is continually shaped by what passes through it. One influential idea about this process is known as the synaptic homeostasis hypothesis. It proposes that waking experiences strengthen many neural connections, and that sleep helps recalibrate some of them. The word recalibrate may bring to mind a stringed instrument resting in a quiet room. After many hours of music, some strings may need a slight adjustment. They are not removed, and the melody is not discarded. Their tension is simply brought toward a useful balance so that the instrument can remain responsive. In a similar way, the sleeping brain may adjust the strength of some connections. If every connection strengthened continually, the network could become costly to maintain. It might demand more energy and leave less room for future learning. By changing the balance, sleep may reduce some of these energy demands and help preserve the brain's ability to learn again. This does not mean that sleep simply erases weak memories. The process is more selective and subtle than that image suggests. Some connections may weaken, while others are preserved or strengthened. The brain is not wiping a slate clean. It is tending a complicated network whose history remains woven into its structure. Nor does this tending occur only during sleep. Cellular maintenance continues during waking life as well. Living systems cannot postpone every necessary task until night. Instead, sleep changes the balance and coordination of that work. Certain processes may become more prominent or differently organized when attention to the outside world has quieted. Another part of the brain's night work involves fluid. The brain and spinal cord are surrounded by a clear liquid called cerebrospinal fluid, often shortened to CSF. This fluid moves around the brain and through spaces associated with it, following pathways too small and intricate to resemble ordinary rivers, yet still capable of rhythmic motion. During sleep, several rhythms can become linked. Slow brain activity may occur alongside changes in blood volume. Breathing adds its own gentle pressure changes. The movement of CSF can rise and fall with these patterns. Human brain imaging has detected large oscillations of CSF associated with slow wave activity, as though the broad electrical tides of deep sleep were accompanied by physical tides of clear fluid. This is a striking observation. Yet careful science makes a distinction between seeing fluid move and knowing everything that movement accomplishes. Animal studies have provided evidence that sleep affects the movement of fluid and dissolved substances through brain tissue. These findings have contributed to what is called the glymphatic hypothesis. This hypothesis proposes that fluid movement along spaces surrounding blood vessels contributes to transport through the brain and to the clearance of certain waste products. The idea is influential and widely studied, but many details remain debated. Different studies do not always examine the same conditions. They may involve different species, different brain regions, or different tracer substances used to follow movement. Some involve anesthesia, which is not the same as natural sleep. Researchers may also use words such as influx, transport, and clearance to describe different parts of the journey. These distinctions matter. Fluid entering a space is not necessarily the same as fluid passing through tissue. Neither is precisely the same as a substance leaving the brain. Each part of the process can be observed and measured in different ways. A mouse study published in 2024 added another careful note to this continuing conversation. Clearance of an injected fluorescent molecule was reduced during sleep and anesthesia. The result did not settle the question. Instead, it showed that the movement of substances through brain tissue may be more complicated than any single simple explanation can describe. For this reason, the familiar statement that sleep definitively washes toxins out of the human brain is too strong. It turns an active area of research into a settled fact. Scientists can observe sleep-related fluid rhythms. They can measure changes in animals and humans. They can form hypotheses, compare methods, and refine their models. But observing fluid movement is not the same as proving that sleep removes a specific amount of waste from the human brain. There is something reassuring in this careful uncertainty. Science does not need to hurry beyond the evidence. It can watch a slow wave pass through the brain, notice a matching oscillation of clear fluid, and remain patient about what the pattern means. Understanding grows through repeated observation, through comparison, and through the quiet correction of ideas that once seemed simpler. The brain's night work is therefore neither a magical cleansing nor a complete renewal. The word reset remains a metaphor. By morning, the brain has not returned to a blank beginning, perfectly renewed and untouched by yesterday. It still carries its history, its habits, its learning, and all the ordinary variations of a living body. Yet something meaningful has changed. Patterns of activity have shifted. Cellular instructions have been read in different proportions. Proteins have been produced. Energy use has been rearranged. Connections have been adjusted. Supporting cells have helped maintain the environment. Blood, breath, slow electrical waves, and clear fluid have moved through linked rhythms. All of this unfolds without urgency. The cells do not know the image of a night shift, yet the metaphor fits their steady coordination. One process begins as another quiets. One signal crosses a synapse, another is softened. A glial cell tends the conditions around its neighbors. Fluid moves through a narrow space near a blood vessel. Across the wider brain, a slow wave gathers and passes, then another follows. The quiet city remains alive. Its streets are calm, its patterns altered for the night. There is no perfect stillness and no sudden restoration. There is only the continuous, coordinated work of a living brain, moving through another phase of its daily rhythm. Among these many adjustments are the changing patterns left by the waking day. There are traces of voices and places, movements and facts, moments and feelings. They are not stored like objects placed untouched upon a shelf. They are living patterns, carried in connections that continue to change. And so, from the maintenance work of the sleeping brain, the night's attention turns naturally toward memory. Beyond the quiet streets, a kind of library remains open, where the experiences of the day may be stabilized, connected, and gradually woven into what the brain already knows. Chapter 6: Sorting Memory and Learning. Beyond the quiet city streets, imagine a library after closing time. The last visitors have gone. Lamps cast warm circles across long wooden tables. Along the walls, Shelves rise into shadow, holding volumes gathered over many years. A few newly arrived books rest on a cart. They have not yet found their places. Some belong beside familiar works. Some contain ideas that connect distant sections of the library. Others may be useful only for a little while. The sleeping brain is not truly a library, of course. Memories are not books, and there are no silent librarians carrying the day's experiences from room to room. Yet the image offers a gentle way to understand part of what sleep supports. During the night, patterns formed through the day can become steadier. New knowledge can meet older knowledge. Some details may strengthen, while others soften into the background. A memory is not a perfect recording. The brain does not preserve each experience as a complete video, ready to be played again without change. Even while an event is happening, the brain selects and interprets. It notices some details and passes lightly over others. Sights, sounds, feelings, meanings, and movements are represented through activities spread across many networks. The memory of a walk, for example, may include the curve of a path, the sound of footsteps, the color of the sky, and the thought that arose beside a certain tree. These parts belong to the same experience, but they are not kept as one untouched object in one permanent drawer. They remain as changing patterns among connected brain cells. At first, many new memory traces are fragile and distributed across the brain. A memory trace is the physical and functional change left in the nervous system by an experience. It may involve altered connections among cells, along with a greater likelihood that certain patterns will become active together again. With time, attention, repetition, and sleep, some of these traces become more stable. This gradual stabilization is called memory consolidation. Consolidation does not make a memory fixed forever. Memories can still change when they are recalled, connected with later experiences, or understood from a different point of view. Consolidation simply means that newly acquired information becomes steadier and more integrated with what is already known. In the imagined library, a new book does not merely receive a shelf number. Its subject must be understood. It may be placed near related works, entered into several catalogs, and connected by references to material in other rooms. In a similar though far more complex way, the brain can link a new experience with older patterns of knowledge. An important structure in this process is the hippocampus. The hippocampus is especially important in forming many new event-based memories. It helps bind together elements of an experience, such as what happened, where it happened, and how one part followed another. This does not mean that a whole memory resides inside the hippocampus. The colors of a scene, the sound of a voice, a meaning of a conversation, and the emotions surrounding it involve wider regions of the brain. The hippocampus is more like a guide that helps bring distributed pieces into relation. It helps the brain establish a pattern that may later be revisited. During non-REM sleep, the brain produces several coordinated forms of electrical activity. There are slow oscillations, broad rhythms in which large groups of brain cells shift together between quieter and more active states. There are sleep spindles, brief bursts of rhythmic activity that appear as delicate clusters on a recording of brain waves. And within the hippocampus, very brief patterns of activity can appear at closely coordinated moments. These rhythms can align. A slow oscillation passes across the sleeping brain. Within part of that rhythm, a spindle appears. Brief hippocampal activity joins the sequence. Scientists continue to investigate exactly how these events work together, but evidence suggests that their coordination supports the reactivation of recent memories. Reactivation, sometimes called replay, means that a pattern related to an earlier experience becomes active again. It is not usually an exact repetition of the waking event. It may be compressed, incomplete, or rearranged. Nor does it necessarily enter conscious awareness or become part of a dream. Much of this quiet revisiting may occur without producing any remembered image at all. It is as though familiar pathways are lightly retraced after the day has ended. A route through a new neighborhood, a sequence practiced on a musical instrument, or information encountered in a lesson may leave patterns that become active again during sleep. Repeated reactivation may help certain connections grow more stable and better coordinated. One leading scientific model proposes that reactivation also helps memories become integrated into wider networks in the neocortex. The neocortex is the large outer portion of the brain, folded into ridges and grooves. It contributes to many complex forms of perception, thought, and knowledge. In the library image, the hippocampus might resemble a temporary guide to the day's new arrivals. while the neocortex resembles the broad system of older shelves and interwoven catalogs. But this metaphor has limits. Nothing complete is lifted from one place and deposited in another. Instead, relationships among many brain regions change gradually through repeated and coordinated activity. This process can do more than preserve individual details. Sleep may help the brain notice what several experiences have in common. Over time, separate examples can contribute to a more general understanding. Several journeys may build a sense of direction. Repeated movements may become a smoother skill. Different conversations may deepen an understanding of a person, a language, or a familiar kind of situation. In this way, sleep can help stabilize useful information, connect new experiences with older knowledge, and draw out common patterns. Learning is not only the keeping of separate moments, it is also the gradual recognition of relationships between them. Sleep supports many forms of memory. These include memories for facts and events, spatial information about places and routes, skills and habits, and forms of emotional learning. Yet no single stage of sleep owns one complete kind of memory. The divisions are not absolute. Both non-REM and REM sleep probably contribute to healthy memory, with their roles varying according to the task, the timing, and the nature of what was learned. Nor does sleep preserve everything. The nighttime library is not trying to keep every passing detail in perfect clarity. The precise shape of every cloud, every word glimpsed on a sign, and every small movement in a crowded room would create an immeasurable collection. Forgetting is therefore not simply a failure. Selective weakening is a normal and useful part of memory. Some details fade while broader patterns remain. A memory may retain the meaning of an event while losing the exact arrangement of minor features. The shelves become not perfectly complete, but more workable, with some pathways clear and others growing faint. This selectivity also means that sleep after learning does not guarantee later recall. Attention, understanding, repetition, emotion, prior knowledge, and many other conditions influence memory. Sleep supports learning, but it does not turn every experience into a permanent record. A night of sleep can help, without promising perfect remembering. As the night continues, REM sleep brings another kind of landscape. During REM sleep, brain activity becomes more wake-like in some respects, and vivid dreams are more common. REM sleep may contribute to the integration of information, emotional memory, creativity, and flexible associations, yet research does not assign it one simple or settled purpose. Recent experiences sometimes appear in dreams. A place visited during the day may return in altered form. A task may be woven into an unfamiliar scene. A phrase, a face, or a movement may reappear, joined to images that never occurred during waking life. Studies have found that dreaming about a recently learned task can be associated with better later memory performance. Yet an association does not prove that the remembered dream itself caused the improvement. The dream and the later performance may both reflect deeper processes unfolding during sleep. Dreams also do not reveal every episode of memory reactivation. Much of the brain's revisiting remains outside the stories remembered in the morning. A pattern can become active again without turning into a conscious scene, an image, or a narrative, and while sleep may help emotional experiences become integrated with other knowledge, it does not always remove their emotional force. Some feelings remain strong. Emotional memory is shaped by many influences, and one night does not make every difficult experience feel distant. The sleeping brain works with what the day has brought, but it does not erase the day. So the library rests through its long, quiet hours. A few pathways have been retraced. New arrivals have found connections with older works. Some details remain clear, while others fade softly into the background. Broader patterns begin to emerge among experiences that once seemed separate. The collection is not perfectly sorted, and it never will be. It is living and changing, gently reorganized each time new experience meets what came before. Facts, events, movements, places, habits, and feelings all take part in this patient process. Some become steadier, some become linked, some are allowed to grow quiet. Nothing is made complete in a single night. Nothing needs to return to a perfectly blank beginning. The brain does not reset by emptying itself. Instead, it continues to adapt, preserving some patterns, reshaping others, and weaving recent experience into the wider fabric of knowledge. Beyond these imagined shelves, the rest of the sleeping body continues in its own nighttime rhythm. As the brain quietly revisits patterns from the day, hormones carry signals through the blood, tissues maintain themselves, muscles and organs adjust their work. The quiet library belongs to a larger house, and throughout that house many forms of coordinated upkeep continue, steady and unhurried, as the night moves gently on. Chapter 7: The Body's Repair Shift. Beyond the quiet library of memory, the larger house of the body continues its nighttime work. Hormones travel through the bloodstream. Tissues attend to their ordinary needs. The heart, lungs, muscles, bones, skin, and digestive organs remain part of one coordinated whole. It is a little like a city after the traffic of daytime has eased. The city has not closed. Lights still glow in important windows. Water moves through pipes. Power crosses hidden cables, and workers tend to streets and buildings. Yet the rhythm is different now. Fewer doors open and close. The crowded avenues become calmer. Tasks that were harder to coordinate during the busiest hours can unfold in quieter surroundings. Sleep gives the body a similar period of coordinated upkeep. This does not mean that repair happens only at night or that every part of the body becomes new before morning. Maintenance continues throughout waking life as well. Proteins are produced, energy is managed, worn components are replaced, and tissues are tended at every hour of the day. The body is always caring for itself. During sleep, however, the conditions change, the balance of hormones shifts, automatic systems settle into a different pattern. Movement is usually reduced, outside demands are fewer, and many parts of the body enter a steadier mode of operation. This is not a complete rebuilding, it is a quieter maintenance shift within work that never truly stops. Much of this shift is guided by the autonomic nervous system. The word autonomic refers to processes that happen automatically, without requiring a deliberate decision. A person does not need to remember to make the heart beat or adjust the width of blood vessels. There is no need to supervise digestion from one moment to the next. These essential functions are regulated in the background. The autonomic nervous system has different branches that help the body meet changing conditions. One branch becomes especially useful when action and alertness are needed. Another, called the parasympathetic branch, is associated with quieter states and often becomes more influential during much of non-REM sleep. As this balance changes, the heart generally faces a lighter workload. Heart rate and blood pressure commonly decrease during much of non-REM sleep. Each heartbeat still sends blood through the vessels, delivering oxygen and nutrients, while carrying away the products of ordinary cellular activity. Yet the pattern is often more settled than it was during the active day. The heart does not stop working, it never steps away from its essential task. Instead, it continues under gentler demands. Steady beat follows steady beat beneath warm fabric, while the breath rises and falls nearby. The breathing muscles also remain active. The chest and diaphragm keep air moving. The brain continues to direct vital functions. The immune system exchanges signals, and cells throughout the body continue to use energy. Sleep is not a condition in which energy use disappears. Even in deep stillness, life requires fuel. For this reason, it can be misleading to imagine one simple energy tank being filled during the night. The body contains many tissues, each with different and changing needs. Energy is stored, released, transported, and used through a wide web of chemical processes. Sleep may help prepare the body for the next period of activity, but there is no single inner gauge that moves neatly from empty to full. The same gentle complexity appears in the body's hormonal signals. Hormones are chemical messengers. They are released in one part of the body and carried through the blood, allowing distant organs and tissues to coordinate their activity. Some hormonal patterns shift with the time of day. They may also vary with meals, movement, stress, age, development, nutrition, and health. Some hormones arrive in pulses, like quiet messages sent at intervals. Growth hormone is one of these pulsing messengers. Its name may bring childhood to mind, when bones lengthen and the body develops. Growth hormone does contribute to childhood growth. Yet its work does not simply end when adult height is reached. Throughout life, it remains involved in protein metabolism and in the maintenance of bone and other tissues. A prominent pulse of growth hormone often occurs soon after sleep begins, in association with early slow-wave sleep. Slow-wave sleep is the deepest form of non-REM sleep. It is named for the large, slow patterns of electrical activity that can be measured across the sleeping brain. This connection is important, but it is not a simple switch. Slow waves do not merely turn growth hormone on as a lamp is turned on in a room. The two are associated within a much larger pattern. Age, sex, developmental stage, exercise, nutrition, health, and individual physiology can all influence growth hormone secretion. The body works through relationships, not through one command sent from one source. Growth hormone is therefore not a magical repair instruction passing through the bloodstream. It is one signal within a much larger conversation. It contributes to conditions that support growth, protein metabolism, bone maintenance, and tissue care, while many other messengers, nutrients, enzymes, and tissues play their own parts. In the quiet city, no single worker restores every road and building. One crew checks a water line, another tends a bridge, somewhere else supplies are delivered, and instruments are read. Each task depends on others, and much of the work began long before evening arrived. Within the body, protein synthesis is one part of this ongoing care. Protein synthesis means building proteins from smaller components. Proteins contribute to much of the body's structure. They also serve as enzymes, receptors, transporters, and signals. Muscles use them, but so do the skin, organs, blood, bones, and immune system. The body builds and breaks down proteins throughout the day and night. Food, physical activity, hormones, health, and rest all influence that balance. Under some experimental conditions, sleep loss can reduce muscle protein synthesis. Sleep loss can also alter patterns of growth-related and stress-related hormones. Findings such as these help scientists understand how sleep participates in physical recovery. But they do not mean that one ordinary night produces a dramatic transformation. Sleep does not guarantee muscle growth, nor does it quickly mend every injury. Recovery depends on the nature of the tissue, the condition of the body, nutrition, circulation, age, health, and many other influences. Sleep supports recovery. It is not a cure for injury or illness. That distinction allows us to appreciate the body's nighttime work without turning it into a miracle. The real process is quieter and more gradual. Some damaged structures are tended. Some cells are replaced in tissues where replacement naturally occurs. Energy supplies are adjusted. Hormonal messages arrive in changing rhythms. The autonomic nervous system helps keep the internal environment within useful ranges. This is coordinated upkeep. It is easy to picture the body as waiting until sleep to begin this work. Yet maintenance never vanishes during waking hours. A person sitting beside a window, walking beneath trees, eating a meal, or speaking with a friend is also producing proteins and regulating energy. The heart is nourished even while it works. Bones remain living tissue. Skin replaces some of its cells over time. Muscles respond to movement, nutrition, and rest across many days. Repair, protein production, and energy replenishment are continuing processes. They do not belong to one stage of sleep, or even to sleep alone. Night does not divide life into a daytime of use and a nighttime of total repair. The boundary is softer than that. Day and night each contain activity and maintenance, but the conditions and proportions are different. During sleep, the relative quiet gives certain patterns room to become more prominent. Early slow-wave sleep is often accompanied by a notable pulse of growth hormone. Parasympathetic influence helps shape a calmer internal state during much of non-REM sleep. The heart's workload generally eases, movement is reduced, and the demands of deliberate action fall away. All the while, energy continues to be used. The heart contracts, breathing muscles move, the brain remains active. The immune system continues its communication. Cells transport materials, maintain their boundaries, and carry out the chemistry required for life. The city is quieter, but it is not dark and empty. Perhaps somewhere in this imagined city a train still moves through a tunnel. A pump keeps water flowing. A warm light remains above a work table. The daytime crowds have gone, leaving space around the smaller motions that continue through the night. So it is beneath the blanket. The body is not motionless in every sense, even when the sleeper appears completely still. Blood circulates, air enters and leaves. Chemical messages travel through hidden pathways. Tissues respond according to their own needs and rhythms. This work is gradual. It is shaped not by a single night, but by continuity across many days and nights. The body does not erase the marks of effort, experience, illness, age, or time. It does not return to a blank beginning. Instead, sleep helps carry life forward, adjusting and tending what is already there. This is the gentler meaning of a daily reset. A reset is not the wiping clean of every page. It is the restoring of useful rhythms. It is the recalibration of many systems, each moving at its own pace. It is a bridge between one period of activity and the next, built through steady regulation rather than sudden renewal. The city will brighten again. Traffic will return to the avenues. Doors will open. Meals will be prepared. Muscles will lift and carry, and the heart will respond to changing needs. Yet beneath that future activity lies the value of hours spent in another arrangement. With reduced external demands, shifting hormones, quieter circulation, and coordinated upkeep. Nothing needs to become entirely new before morning. The body only continues its patient care. For now it remains held in quiet continuity beneath the blanket. The heart keeps its steady passage. Breath moves gently in and out. Warmth rests along the skin, while countless ordinary processes continue beyond awareness. The maintenance shift is not limited to muscles, bones, or skin. In these same quiet hours, immune signals and metabolic rhythms continue their slow exchange of information, carrying the body's coordinated care into another part of the night. Chapter 8: Sleep, Immunity, and Metabolism. The quiet exchange of information continues through every hour of the night. No single system works alone. The immune system listens to signals from the brain and body. Metabolic organs respond to patterns of activity and rest. The heart and blood vessels adjust to changing needs. Hormones rise and fall according to schedules shaped by both sleep and the internal clock. Together, these systems are less like separate machines and more like a landscape crossed by many gentle currents. A change in one current may influence another. Sleep belongs within this landscape, not as a cure or a simple switch, but as one of the regular conditions under which the body coordinates its work. Consider the immune system, the broad network that recognizes injury, responds to infection, and remembers some of what it has encountered before. Its workers are distributed throughout the body. Immune cells travel through the blood and lymph, gather in tissues, and pause in places such as lymph nodes, where information can be exchanged. Their movement is not constant at every hour. Different immune functions become more or less active at different times of day. Some cells circulate more widely during one part of the daily cycle, while others enter tissues or gather in particular regions. These patterns are influenced by sleep and also by circadian timing, the roughly 24-hour rhythm that helps organize the body's day. It is difficult to separate these influences completely. Sleep usually occurs at a particular circadian phase when the internal clock is already guiding temperature, hormones, digestion, and alertness toward their nighttime patterns. A person sleeping at night is experiencing both sleep itself and a particular point on the circadian clock. Researchers distinguish these influences when they can, but in ordinary life, the two remain closely woven together. The immune system and sleep also communicate in both directions. Sleep affects immune activity, while immune activity can affect sleep. This becomes familiar during an infection, when a person may feel unusually tired or inclined to rest. Part of that feeling can arise from cytokines. Cytokines are signaling proteins used by immune cells and many other tissues to carry instructions. They help coordinate responses across a distance, rather as short messages might pass between different districts of a quiet city. There are many kinds of cytokines, and they do not all perform the same task. Some encourage inflammation, some help limit it, others guide the growth, movement, or behavior of cells. During an immune response, certain cytokines can act on the brain and promote sleepiness. They may also alter the structure of sleep, changing how time is distributed among its stages. This does not mean that every night follows a single immune plan, or that sleepiness always reveals exactly what the immune system is doing. The exchange is more subtle than that. The body adjusts according to the signals present, the time of day, previous sleep, age, health, and many other conditions. Its rhythms are responsive rather than rigid. During ordinary sleep, immune cells continue to move, communicate, and prepare. Sleep appears to support parts of adaptive immune memory. Adaptive immunity is the branch of immune defense that learns to recognize particular targets. After encountering a pathogen, or after a vaccination presents the immune system with a form or part of a target, certain cells can retain useful information. If the same target appears later, the response may be faster and more focused. Sleep around the time of vaccination has been associated in some studies with aspects of the later immune response, yet the strength and details of this relationship vary among studies, individuals, vaccines, and circumstances. Immune memory depends on many factors. Sleep is one participant in the process, not the only author of it. Still, the general image is helpful. During quieter hours, immune information can be sorted and reinforced within a body whose external demands have changed. Cells meet in tissues. Chemical messages travel. The internal clock marks the hour. Sleep provides a recurring setting in which parts of this communication can unfold. Nearby, metabolism follows its own changing rhythm. Metabolism is the name for the many chemical processes that obtain, store, transform, and use energy. It includes the handling of nutrients from food, the building and renewal of tissues, and the release of energy that allows cells to perform their work. Metabolism never simply stops. During sleep, its priorities and pace shift. The body is still using fuel. The heart continues to beat. The muscles of breathing continue their gentle movement. The brain remains active through changing sleep stages. Cells maintain their boundaries and tend to ordinary wear. At the same time, the absence of eating and most physical activity creates a different metabolic setting from that of the active day. Hormones help coordinate this setting. Insulin, for example, helps cells respond to glucose, a simple sugar that serves as an important source of energy. The way the body regulates glucose changes across the day and night. It is influenced by meals, activity, circadian phase, and sleep. These influences overlap so closely that timing matters as much as any single event. Sleep duration, continuity, and timing can all be associated with the way the body handles glucose. A disrupted or unusually short night may temporarily change insulin sensitivity, which means how readily cells respond to insulin's signal. Yet bodies vary, and one night is not the whole story. Metabolic health emerges from patterns across time, together with movement, food, genetics, age, environment, and many other parts of life. Appetite is also guided by several interacting signals. Hormones and nerve pathways report whether energy is available, whether the stomach and intestines contain food, and whether stored reserves are sufficient. Two often discussed hormones are leptin and ghrelin. Leptin is produced largely by fat tissue and participates in longer-term signaling about stored energy. Ghrelin is produced mainly in the stomach and can contribute to hunger. These hormones are sometimes described as a simple pair, with one bringing fullness and the other bringing hunger. The real system is more complex. Appetite is shaped by many chemicals, sensory cues, habits, emotions, food availability, and the circadian clock. Sleep can influence this network, though it does not control it by itself. Once again, regulation is shared. The heart and blood vessels take part in the same nightly arrangement. During much of non-REM sleep, especially during deeper sleep, heart rate commonly slows and blood pressure tends to fall. This nighttime lowering of blood pressure is sometimes called dipping. It reflects changes in the autonomic nervous system, the system that automatically adjusts functions such as heartbeat, blood vessel width, and digestion. One branch of the autonomic nervous system supports alert activity and rapid responses. Another supports quieter maintenance. Both remain available throughout the night, but their balance changes with each stage of sleep. During non-REM sleep, cardiovascular activity is generally steadier. During REM sleep, it can become more variable, accompanying the brain's shifting patterns and vivid dream activity. The circadian clock also influences the cardiovascular system. It helps organize daily rhythms in blood pressure, heart rate, hormone release, and the readiness of blood vessels to respond. As morning approaches, these signals begin to change in preparation for waking and movement. The heart does not wait passively for the eyes to open. It follows a gradual timetable, adjusting before conscious activity returns. All these rhythms, immune, metabolic, and cardiovascular, cross one another like paths through a quiet garden. Cytokines carry messages between immune cells and the brain. Hormones carry information about fuel and timing. Nerves adjust the heart and blood vessels. Light received earlier in the day helps set the circadian clock, and that clock lends order to events occurring many hours later. The word reset can still be useful here if it is held gently. The body does not erase yesterday's immune encounters or empty every store of energy. It does not return the heart, appetite, or blood sugar to one perfect starting point. Instead, it continually recalibrates. It preserves memory where memory is useful. It shifts fuel between storage and use, It changes circulation to match the needs of each stage. It prepares for what usually comes next. Nor is every night identical. Sleep changes across a lifetime. It varies from one person to another, and from one season of life to the next. A late meal, an unfamiliar room, physical exertion, stress, illness, caregiving, travel, or simple chance may alter the pattern. The body works with these variations rather than demanding flawless repetition. Its coordination is flexible. A brief awakening may pass through the night. A period of deep sleep may give way to lighter sleep. Immune cells continue their travels. The liver tends its stores. The pancreas responds to chemical signals. Blood moves through branching vessels, reaching every warm and living region. From the outside, little of this can be seen. There may be only a quiet face, a softened posture, and the small repeated motion of breathing. Within, timing continues to matter. Messages are received and answered. Some processes become more active while others recede. The body does not become silent. It simply changes its manner of conversation. As the night continues, that conversation moves toward another landscape. The steady depths of non-REM sleep alternate with periods when the brain becomes more active, the eyes move beneath closed lids, and dreams may gather into vivid forms. Immune rhythms, metabolism, heartbeat, and breath remain present there too, accompanying the sleeper into the shifting world of REM.